And I'm going to review, and I'm going to go more slowly now. So I've gone through the first 3 chapters quite quickly. I'm going to slow down a bit because we're getting into material that you may not have you may not have seen yet. So I'm going to be going more slowly now. And of course, the subject here is Fourier transforms, and let me give you the skinny on it. I'll give you the skinny and then I'll work through it. And the skinny is that delta of x minus y can be written as a decay from minus infinity to plus infinity, e to the I k x minus y, and over 2 pi. And this is a formula that I hope you've seen before. It's, I'm trying to get blue because I think blue shows up better than green. Oh, and let me get rid of this. And also, oh, let me get rid of this thing that just constantly appears where it shouldn't. So annoying. Okay, so now you see this standard formula for the delta function. And this is, of course, a continuum version of a delta function that you saw earlier in, I'm looking it up here. Well, when we did Dirac's comb, and that was basically a delta function, although it was really an infinite sum of delta functions. So here, for example, we can say that f of x is the integral of f of y delta of x minus y dy, and this then will be f of y integral, wow, what has happened here? Oh my God. It's the trouble with these touch-sensitive screens is that they... Okay, so this is then an integral dy from minus infinity to plus infinity. And then this delta of x is an integral minus infinity to plus infinity dk over 2 pi e to the I k x minus y. And so rewriting that, what we've got is that this is an integral dk. Let me see, dk e to the minus I k y. Oh, wait a minute. I want to make this an integral. Right, I want to do the dy integration. So hold on, I shouldn't do these things in real time because I sometimes screw up. So we want this to be dy over 2 pi e to the minus I k y of an integral dk over, well, let's put a square root of 2 pi here. Square root of 2 pi, and this is going to be e to the no, this should have been plus ik. Hold on. X e to the minus. e to the minus iky f of y. And so now we can rewrite this as integral dy. No, I've gotten it backwards again. No, I'm going to make this a dk. So hold on. Dk over square root of 2 pi. I'm going to call this f of k, or f tilde of k, and e to the I kx, and then f tilde of k is the rest of this. F tilde of k will then be an integral dy over square root of 2 pi e to the minus I ky f of y. So I've decomposed here, let me switch to red here. I've decomposed this thing into two factors, this and this factor, which is over here. So, well, that's a sort of lightning introduction to Fourier transforms via the delta function. Why don't we just do it in a straightforward way? The point is that if we have a Fourier series of length L, say from minus L to plus L, then here, I can make this a little bit bigger, I think. What we notice is that these phases, because of the 1 over L, are essentially the same if we replace n by p, where p is within a half of n. So in other words, instead of here we have a sum over n, and for each n we can consider, instead of summing over n, we can integrate over this interval from n minus a half to n plus a half, and we can integrate not over n, but over p replacing n, as long as p is close to n. Christ. And there's a mathematical function that does that for us. It's called the closest integer function, or the nearest integer function, which is just the square bracket symbol like that. So for example, square bracket p is n if p minus n is less than a half. So it's that n that is selected. Or if you want, well, let's just say less than a half. Remember, think of integration and summation and so forth as integration in the Lebesgue sense, so you can always forget about any particular real number. So what happens is we stretch this interval, then the difference between e to the I 2 pi nx over L and e to the I 2 pi px over L, as long as p is close to n, this is negligible. And so we can rewrite this in this form. And if we formalize it by saying that we set fn, f sub n to f hat of p, where f hat of p is f sub greatest integer, nearest integer of p. Well, that just is no change at all. We haven't changed anything. It's exactly the same. And so now our function that originally was this now turns into a sum over all the intervals, integrating dp of f hat of p, and well, summing over the integers and integrating over each interval just means we're integrating p from minus infinity to plus infinity. And now, since the difference is negligible in the phases, effectively we just have an infinite integral like that. So we've expressed f of x as a Fourier transform of f hat of p. And so now we do a change of variables, and the change of variables is absolutely necessary because we want to get rid of this square root of L. And so what we do is we change from P to K, which is 2 pi P over L. And so then dP is LK over 2 pi. And so this thing turns into L dk over 2 pi, the square root of L, the f hat. P now is LK over 2 pi. And we basically have this expression here. So now we just redefine this thing. Square root of L over 2 pi f hat of LK over 2 pi. We say, well, that's our new function, f tilde of k. And so now we have expressed f of x as f tilde of k to the ikx dk over root 2 pi. So that's a derivation of the Fourier transform. Now we have to trace back through this chain of definitions, each one simple, but when you put them all together, they become confusing, at least in my mind. So to find f tilde of k, we have to go backwards, and we say, well, f tilde of k has to be this, and f hat of y is f of the nearest integer to y. And remember that we have this inequality, which, now that I think about it, is a little bit, at least a little bit confusing here. Let me see if I can actually fix this on the fly, because what's actually going on here is a parenthesis here and a parenthesis there. I think that makes it clearer. And so what we then have is that f tilde of k, which starts out as this, then f sub nearest integer to LK over 2 pi, well, that is by just as an ordinary Fourier series term, it's this integral. And then the square root of L's cancel, and you simply have this. Now you take the limit L going to infinity, and you find that you get that the inverse Fourier transform looks like this. So that what we've derived then is these Fourier transform relations, that f of x is an integral of f tilde of k to the ikx over root 2 pi, and f tilde of k in turn is the integral of f of x e to the minus ikx dx over root 2 pi. And let's sort of remember here how we got from there to there. Well, we have to go back to the formula 3.42 to remember what f sub n is, and that, so I'm trying to find that on a different Right, okay. So here I'm going to blow this up. And I'll bring it over to this screen. What our old definition of f sub n was this. So that's how we find out what this thing is. Namely, it's just this integral. Here, the interval is 0 to L. It's now minus L over 2 to L over 2. But so that's I think I should have repeated that definition there. Let me write a note to myself, repeat 3.42. So that's basically the derivation of this. Of course, the quick definition is just use Dirac's formula here for the delta function, and then everything is automatic. So that's the marvelous thing about one of the marvelous things that Dirac's done. He's introduced a concept and a notation, and using that concept and notation, everything becomes, not everything, but a whole variety of things become automatic. Now, just as in the case of Fourier series, you've got you have a plus sign here and a minus sign there. Well, that's not important. This could be a minus sign, and that could be a plus sign. And you got a root 2 pi here and a root 2 pi there. If you're doing things, if Fourier transforms are new to you, just use these formulas in maroon and don't screw around with anything else. On the other hand, once you become familiar with this, then you can use plus here and minus there, or you can use minus here and plus there. You can put the 2 pi's over here, or you can put the 2 pi here. It really doesn't matter, but you just have to be consistent, as with Fourier series. So let's see, we have a chat thing here. You can if you want me to go over something again, put it in the chat. And in fact, you can catch my attention even better if you just use capital letters, hit caps lock and type that way. And then it'll be a little easier for me to notice. Now, what you sometimes need is the relationship between a Fourier series and a Fourier transform. And so we can go through that. That's a little bit confusing because it means keeping track of a lot of different definitions. And that means you have to keep minuses and 2 pi's and i's and everything straight. And that's always confusing. But if we just go through it, what does the Fourier series look like? Well, the Fourier series looks like this on a finite interval. We're also writing it as a Fourier transform, and we can imagine we can set Kn equal to 2 pi n over L. It looks like this, and then the transformation from there to there is sort of straightforward. F sub n is f hat of p according to these definitions, where f is f sub nearest integer to p. And then using that and using our definition, here, this thing, there's the definition of f tilde of k. We can rewrite that as we get f hat, that's f hat of p, that's f hat of p is lk over 2 pi, and that's related to f tilde in this way. And so to get the Fourier series from the Fourier transform, you have f of x and you go like that. So the Fourier series, if this is the Fourier transform function f tilde of k, you just use f tilde of k sub n, where K sub n is the K, is the K that's closest to n, and square root of 2 pi over L. Then to go to the other way, if you have the Fourier series, the function f of x looks like this, where these are the Fourier coefficients, and you're integrating, and you have these L's like that. So what bothers me a little bit about this formula is it looks as though it diverges in the limit L going to infinity. And I guess what saves us is that this f hat is really f tilde over square root of L. Anyhow, last time we did the Fourier transform of Gaussian, maybe I'll go through that quickly because we already did it. The Fourier transform of a Gaussian is a Gaussian. That's the important thing to know. Also, something that's very important with regard to Fourier transforms of Gaussians is you basically get the answer. The important part of the answer comes about almost immediately, because what you do, f tilde of k, you just complete the square in this exponent. And when you complete the square, the k pops out, and then you have a k here. And the important thing to know is that this k is no longer functional. It doesn't mean anything because, as I said last time, the integral of an analytic function, so f of z, integral of f of z dz is 0 if you go along a, well, here, let me get rid of that 0 and write a decent 0. It's 0 if you go along a closed curve in the complex plane in a region of analyticity, and the curve and everything inside the curve is inside a domain of analyticity. So if you have any poles, they're out there. Any lack of analyticity, it's out there. And so that means that the integral along here, the integral up here, the integral down there, this is all 0. But on the other hand, this integral and that integral then have to cancel, because these two integrals, in the case of a Gaussian, they're essentially 0 because they're weighted by e to the minus m squared x squared. So they vanish. And so this one is going in the opposite direction, so it has a minus sign. So the only way that this integral can vanish is if integral that way is equal to integral this way. And that's saying then that the integral, in other words, so I'll switch maybe to red, that the integral along here and the integral along there and the integral along there, anywhere, any horizontal integral from minus infinity to plus infinity, and it's a dx here, of this function is going to vanish no matter what k is. K is just this distance here. So this is k, this is another k. Here's another k, that's k equal to 0. That's k greater than 0, that's k less than 0. These integrals are all the same. So we can drop k. So that means that the whole k dependence of a Gaussian integral is obtained by completing the square. And completing the square is something that's very simple to do. You just figure out what you need to do to see. What you've got here is you need to add something that cancels this phase factor. And the thing you add that cancels the phase factor is this structure here. The m squareds cancel, and the 2 gets canceled by this 2, and the phase factor goes away. Then you get something like this. And then this is just an integral, and that's just a number now. It doesn't have any dependence except for the m. And so it turns out that the actual value of that integral is square root of 2 pi. So what you've got is just the prefactor, the m, and e to the minus k squared over 2m squared. So at any rate, one of the things, we'll go through the complex variable theory in a couple of weeks, but the thing to keep in mind right now is that completing the square in exponentials is really important, really easy, and gives you a lot of information. And so what we found is the Fourier transform is a Gaussian. And as I said to you last time, that if m is small, then f tilde of k is a very sharp Gaussian. Whereas if m is big, it's Fourier. So in other words, if m is small, as a function of e to the minus m squared x squared over 2, this is, if m is small, this is very smooth. And this is, this picture here, very smooth. On the other hand, this is when x is very smooth, but then e to the I kx here, the f of k function, it's Fourier transform. Fourier transform of a smooth Gaussian is a very sharp Gaussian. And the Fourier transform of a sharp Gaussian, e to the minus m squared x squared over 2, where m is big, is a smooth Gaussian. So this is something to keep in mind because it shows up a lot. There's a lot of physics that depends upon nothing other than that. Then you can invert f tilde of k and see that you get back to the original one. And so in other words, to get back to f of x, well, it's f tilde of k to the I kx over root 2 pi. F tilde is e to the minus k squared over 2m squared over m. Then you complete the square like this. The k doesn't, the x doesn't matter in this case. And so you just have this thing, which is a number, and the number turns out to be 1 when everything's done. And so you get back to e to the minus m squared x squared over 2. You can also see how you can represent a Gaussian as a Fourier series. And you can also generalize Gaussians. In other words, e to the minus g squared, g of x squared over 2 can be written as this kind of a Fourier transform. And that then is an integral that looks like this. Now that we know what a Fourier transform is, we can go to the special case of a real function. And then if f is real, well, we take the complex conjugate of f tilde, and what we get is minus I kx turns into plus I kx. On the other hand, letting k go to, or letting, k go to minus k, we then have e to the minus I kx, and so that's f tilde of minus k. And so the rule is that f tilde star of k is the plus sign here means that is the same thing as having a minus sign there to turn that k into a plus sign. So it's f tilde star of k is f tilde of minus k, or equivalently f tilde of minus k is f tilde of k star. And consequently, you can see that if you have a real function, you can write it in terms of cosines and sines like that. And Now, Dirichlet introduced his square wave that is, it's sort of the opposite of the theta function. It's sort of theta of -1. I don't quite know. Oh, I'm sorry. This is not, this is Dirichlet's function. And this is where this is 0. So this is Dirichlet's function. And you can write it in this way if you want. The Fourier transform of an even function looks like this, and this is even, and the Fourier transform of an odd function then is odd. I guess that's kind of obvious. Okay, so now we go back to Dirac, and it's amazing that you could almost throw away everything everybody wrote except for what Dirac wrote, and you'd have a good fraction of the important things in physics. So f of x is this integral, its Fourier transform relation looks like this. And now we write f tilde of k as the Fourier transform of the original function. Then we combine the two and we get this. But this is the same as a delta function equation. And so that means that this delta function has to be what's in the curly brackets here, the huge curved brackets. And that says that delta of x minus y is this integral dk over 2 pi to the ik x minus y. Of course, that's what I started with this lecture with, and now we've come back to it. The remarkable thing about computers and MATLAB and so forth is that you can verify things like this and see how remarkably true they are. And so this, we can approximate this by going from -n to +n and doing the integral explicitly. We get sine n x minus y over pi times x minus y. Now I've computed that. I set to get just the delta of x, delta sub n of x. So delta sub n of just x then is sine nx over pi x. And so I computed this for capital N equal to 1,000,000, y equals 0, and plotted it. And this is what I got with MATLAB. And what I want you to make sure to realize is that the difference in scales between the y-axis and the x-axis is a factor of 10 to the 8th, 100 million. So in other words, this actual formula resembles Dirac's delta function better than this drawing by a factor of 100 million. Okay. So in other words, this Dirac's formula here is really golden. I don't know, this damn thing, it's just, oh my God, now I've gone to the beginning of the stupid. Okay, this formula, which you might say, oh, I don't know if I can trust that thing. Well, here's a picture of it, and just setting n equal to 1,000,000, which, you know, you consider the amount we spend on weapons, $1 trillion each year. This is more guns and spies altogether. This is just 1,000,000, and the actual delta function is better by a factor of 10 to the 8th because this is 10 to the 5th and this is 10 to the -3. So we can write f of x as the integral of the delta function, and we can write the delta function this way, and then we get doing the K integration, we get F tilde of Y. So the delta function gets us right back to the Fourier transform, which is what I started the lecture with. Remember, we have a chat board. You can type in a question, and if you use capital letters, it'll be even more obvious to me. Mathematicians define the inner product of two functions as this: f star of x, g of x integrated dx. And it's, the mathematicians write it this way. One can write it in Dirac notation that way. However you write it, looks like this. It's an integral dx, and if we write it in terms of Fourier transforms, we have here, and we have to star the f. So this is f written in terms of its Fourier transform, and then complex conjugated. Here's g written in terms of its Fourier transform. And now we put them all together, and we see we have an integral dx, k prime minus k over 2 pi. That's delta of k prime minus k, and that gives us this integral. So we get what's called Parseval's relation, which is the integral of f star g over x is equal to the integral of f tilde star g integrated over the Fourier transform variable. And so that means that the inner product of two functions is the same when expressed in terms of the functions or in terms of their Fourier transforms, which is what this is saying. This, I think, is a good place to introduce, to tell you about delta functions of more complicated arguments. And this is something that pops up in all the time in physics, because in physics, we don't find just delta of x, we find delta of g of x. So what is that? Well, first of all, let's assume that g of x only has 1 0. It only vanishes at x0. And that the derivative of g at x0 is not 0. Okay, so this integral j really is sensitive only to f of x when g is essentially 0. Oh, hold on, we've got a question. Well, okay, the question was, what's the use of delta functions? Well, it turns out that these delta functions are just used just all the time in physics. And in particular, in field theory, if you're considering the electromagnetic field, either the classical electromagnetic field or the quantum electromagnetic field, you write it as Fourier transform. What's the Fourier transform? The momentum. What's the momentum? It's the momentum of the photons in the electromagnetic field. And so the transformation from the electromagnetic field at x to its Fourier transforms takes you from what the field is at x as measured by a voltmeter, and then what it would be measured, what the field is when measured by a counter, like a Geiger counter if you have high energy photons. So it's just all over the place. Later on in this chapter, in fact, I might even see if I can zoom there quickly. Let's see. I don't remember all this immediately, where everything is. Oh. I don't know, did I stick it in this chapter? Well, all right, let me just give it to you straight. I said the electromagnetic field, but any old field. phi of x is going to be an integral dk, something like square root of 2 omega k or 2 pi omega k. I don't know, it depends on the notation. An annihilation operator, a phase factor, a creation operator, and here these annihilation and creation operators if they're bosons, they have a delta function commutation relation, and by this is meant A of k, a dagger of p minus a dagger of p, A of k is equal to that. If they're fermions, then it's A of k, and I have to put a spin index here because if you have fermions, then you necessarily have spin. So delta ks, delta k minus p. So that's you have these the annihilation creation operators, and you write the field like that. And if it's a fermion field, then psi of x is a sum over spin integral over k, and A of k and s e to the I k x. Oh, and then you need a spinner here. So let me switch here and put in an damn it, an epsilon of k and s plus a dagger of k and s e to the minus I k dot x epsilon star of k and s. And here actually, for the kind of fermions we know, they are typically Dirac fermions, and then this is a creation operator for the conjugate particle, the particle with the opposite charge. So in other words, for the electron field, this annihilates electrons, and this one creates positrons. So minus electrons plus positrons. All right, well, that was a big diversion from what we were supposedly talking about. So let's go back to this. Anyway, as I said, they just occur all over the place. So what I was trying to explain here was, what do you do? Oh, thank you. What I was trying to explain here is that if G only vanishes at a single point and it vanishes in a non-trivial way, having only 1 0 there, or in a trivial way, having only 1 0, depending on your point of view, then this integral is only sensitive to f when f is near x0. So we can pull out f of x0. And then what we have is this. And now g of x, it's sensitive only to g when it's near its 0. And near its 0, it's just g prime of x0 times x minus x0. So it really looks like that. But then what you can do is you can multiply and divide by the absolute value of g prime of x0, which is what we assumed was non-zero. And if we do that, we get a g prime here and a g prime there. On the other hand, this thing here is effectively dg, since the delta function is non-negative. And so this is delta of G minus G0, where G0 is well, G0 is actually 0 now that I think about it. And this then is, whether you say G0 is 0 or not, it's unity. And so that's f of x0 over G prime of x0. So putting all this together, what we have is that the original function, which we call J, so there's the original function, is J, and J is f of x0 over G prime of x0. And so another way of saying that is that the delta function of G of x is just the delta function of x minus x0 over G prime of x0. And so the reason why that's, let me get rid, oh, Jesus. All right, how do I get back? I go back to there and I get rid of that. Okay, so now we can see things a little better. I'm going to switch to blue. Okay, I've switched to blue. I've forgotten what I was going to do. What did we just, oh, we just did the, how to evaluate these. So what we found is that delta of G of x is equal to this. So in other words, the integral of G of x, a delta of G of x, f of x, is if there's only one, if G only has 1, 0, then it's f of x0 divided by G prime at x0. But if G has several zeros, then we have to do a sum like that. Then there is a subtlety here that's rarely mentioned. In fact, I've never seen it in the literature, but on the other hand, I haven't read everything. What if G prime at x0 does vanish? Then what happens if we integrate over x0? Well, we can replace G of x with a half x minus x0 squared G double prime. And then we can let y equal to x minus x0 squared over 2. And so this then is delta of y G double prime of x0, f prime of x0. And now we can just use our old formula, namely that we just have a delta function, a more complicated delta function. And so that means we have to divide by the absolute value of G double prime at x0, and we multiply by f prime of x0. So in other words, if x0 is the only root of G of x, and G of x0 and G of prime of x0 is 0, then delta of G of x looks like that. And there are two examples of that we'll encounter later on. And this is the formula we use in this special case. If we set y equal to 0 in the Dirac comb, we get this expression, and integrating over it, we get that sum. And that gives us what's called the Poisson summation formula, namely the function evaluated at 2 pi L summed over L is equal to 1 over root 2 pi, the Fourier transform evaluated at N. N and L are both summed over the integers. And in the stretched version, what you get is this expression. And an example of that is that you can, if you're summing e to the minus k squared over 4m squared, you can rewrite it apart from this factor as e to the minus 2 pi L m squared. And there's actually some utility. This is useful if you're doing something numerically, and suppose m is very small. Well, then it'd be really great to use this formula because you'd only have to do the first few terms, whereas here you'd have to sum out to the 50th term. On the other hand, if m is very small, well, you don't, if m is very large, then you don't want to use the left-hand side, you want to use the right-hand side. So, and this technique has been, is called Ewald summation. It's a way of summing electrostatic energies that fall off with only a power of the distance you sum their Fourier transforms. So there's a reference there to where, well, you can look in the back of the book. Anyway, what about derivatives and integrals of Fourier transforms? Well, this is the Fourier transform, f written in terms of its Fourier transform. And if you differentiate it, you get an IK. So differentiation corresponds to multiplication by IK. So this is one of the many uses of Fourier transforms, namely that they turn something that's kind of tricky, differentiation, into something really trivial, multiplication. And differentiating twice, you get minus k squared, f tilde, n times ik to the n. And you can even integrate. So now, if you integrate the function, what does that mean? Well, it means you are integrating the indefinite integral, and we're not counting surface terms. So you just integrate that once, and that corresponds, oh God, what do I have to do to make this bigger? Oh, yes. Okay, that corresponds, integrating once corresponds to dividing by ik. So over here, differentiating, you multiply by ik. Integrating, you divide by ik. Integrating n times, you divide by ik to the n. So those are, I mean, differentiation is already a hell of a lot more complicated than just multiplication by ik, but integration is much harder than differentiation, and integrating n times is, you know, a real problem. But all you have to do is divide by ik to the n. But of course, this works only if you're integrating. If you're integrating the well, I guess, yeah, that is right. That I was about to say you have to integrate over everything, but that's what we just did. This is the hard part, integrating symbolically, and it's just a Fourier transform of 1 over ik to the n times the ordinary. Anyway, so that's really another advantage of Fourier transforms. I haven't really seen any applications of that. In fact, I haven't seen these formulas in literature at all, but I haven't read very much of the literature. Anyhow, momentum and momentum space. So this is something that presumably you've learned in quantum mechanics in college or graduate school. We can write a wave function as in terms of its Fourier transform, and if we change variables from k to p, bringing in h bar just to make sure that our notation is as complicated as possible. Parseval's relation tells us that the integral of the absolute value squared of the wave function over x is an integral over p of a related wave function, which we call the momentum wave space wave function integrated over p. And then that Parseval relation says that the inner product of two states can be written either in x space or in momentum space. The outer products of x and p can both represent the identity operator. The Fourier transform connecting the momentum space wave function and the position space is given by, it takes this form dp over root 2 pi h bar. The inverse Fourier transform looks like that. In Dirac notation, this equation looks like this. So you see what Dirac does is just give us an instantaneous way of deriving these things. You just put in the identity operator. P psi is phi of p, xp is this, and so then we realize what xp is. The delta function is the inner product of x with y, and that's this, which again gives us back Dirac's basic delta function formula. And if we differentiate, well, h bar over I is just p, and so what we've derived is this famous thing in quantum mechanics that might seem strange to people initially, namely that the momentum operator is represented by h bar over I d by dx. And in Dirac notation, that looks like this. H bar over I d by dx of psi is p, the operator in between the two states, x and psi. Putting in another identity operator, p prime is an eigenstate of p with eigenvalue p prime. And so we're left with just x, but with p prime with x p prime, which is this phase factor over the square root, and p prime psi, which is phi of p prime. So that's how these things work together. The uncertainty principle, by the way, I don't know if I told you this, but I once met Heisenberg in Berkeley. Oh God, it must have been 45 years ago. Anyway, he was a nice man. I didn't talk with him very much, just shook hands. Anyhow, let's first normalize the Gaussian to unity, and we use this relation, this Gaussian integral, to normalize it. So here is our wave function. It's a wave function for a particle that's centered at the origin with sort of an uncertainty of the order of A. Let me get, see if I can get rid of that. So this is the wave function at the origin. The mean value or average value of an operator in a state psi. Dirac's term is average value. I think that's better than mean value. I used mean value. I got mean value from Gelman, who remarked that the term expectation value is an abuse of English, and it was introduced by a German physicist whose familiarity with English was modest. And so I have been imitating Gelman and using the term mean value, but then a colleague here pointed out to me that Dirac actually used the term average value, and instead we went from average value to the stupid form expression expectation value. We should really stop using that and use correct English to make everything simpler and understandable. So the average value of an operator in a state psi is psi, the operator psi. And that's if the system isn't a pure state psi. If, on the other hand, it's more generally described simply by a density operator, then the average value of the operator A is the trace of rho times A. And this Gaussian here is an even function of X, and so the average value of the position operator vanishes if, in this state at least. The variance of an operator is the average value of the square of the difference between the average value of the square of the operator minus its average value. And so that is given by this expression. And now, if you write this out, what you see is that there's a cancellation. You get, what you get is, you have trace rho A minus A squared. So this is trace rho A squared minus 2 trace rho A plus trace rho A squared. Well, the density operator, which I should have mentioned to you, has several properties. It's non-zero, or it's non-negative, which is to say the average value in any state, S rho S, any state is always non-negative. The trace of rho, which is the sum over a complete set of states of n rho n, is equal to unity, which means that this is the probability that the system is in state n, and it's got to be in some state, so they have to sum to 1. And the other thing is that rho is a Hermitian operator. And well, I don't know. I forget the argument there, but the idea, you can write it in terms of, well, all right, let me, anyway, it's a Hermitian operator. I suppose one way of thinking about it as a Hermitian, if this thing is true, then it's for any state, then it's automatically Hermitian, I think. Anyhow, what I was trying to show you here is that since the trace of rho is unity, this thing here, let me see if I can shift to red and work this out for you. That doesn't change, but this is trace rho A. This is effectively minus 2 trace rho A squared. And so combining these two, they're equal to minus trace rho. Well, trace rho is itself that, and so this is just absolute value of A squared. So right. So the variance then, which is A minus this is then the average value of A squared minus the average value of A squared. Anyway, back to this business here. Delta of x squared is then this. X turns out to be 0 here. We just argued that because the wave function is centered at the origin and symmetrical. You do the integral, you get A squared over 4. You can use a Fourier, compute the Fourier transform of the wave functions, the Fourier transform of a Gaussian. You find that it is, of course, another Gaussian. And that Gaussian is given by this. Then we find that the variance of p squared, well, that's just the average value of p squared. And that turns out to be h bar squared over a squared. And so we have an example of Heisenberg's uncertainty principle. Delta x squared, delta p squared is h bar squared over 4, or delta x, delta p is h bar over 2. So this is the Heisenberg uncertainty principle, and it's much more general than that. It's that if the commutator of x of two operators is greater than or equal to h bar, then the product of their variances is greater than or equal to h bar over 2. . anyway, if the state of a free particle at time zero, well, we can express it in terms of momentum eigenstates. If it's a free particle, it just evolves according to the free Hamiltonian. So at time t, it's equal to e to the minus I h t over h bar on that. When h hits p, it turns into p squared over 2m. And so what we have left is this structure doing the integral. Well, we can't do the integral if you don't know what psi is. There's something called the characteristic function. And the characteristic, suppose we have a probability distribution. Well, it's non-negative, you integrate it, you get unity. The characteristic function, by definition, is the Fourier transform of the probability distribution. And I think I'm going to change expected to average. The average value of a function is its integral over the probability distribution. And that gives us the average value of the phase factor then is the characteristic function. And in particular, the moments of a distribution, x to the n p of x, the average value of x to the n is are derivatives of the characteristic function. Apparently, this term expected has lingered in statistics, unfortunately, and it's an unfortunate abuse of language. Fourier transforms of several variables. Well, just as for Fourier series, you just do the same thing, namely f tilde of k1 and k2. Well, it's just a double Fourier transform of f of x1 and x2, e to the minus I k1 x1 minus I k2 x2. And if you then write f in terms of its Fourier transform, you can see that if you use the double Fourier transform to compute what f of x is, you can see that with the delta functions, you get it back again. So once again, it's all just basically Dirac, and he brings everything back to us. So f of x1 and x2 is the Fourier transform of its Fourier transform. And the Fourier transform of a function of n variables looks like this. Look at 2 pi raised to the power n over 2. The inverse is, again, 2 pi to the n over 2, but now e to the plus I. And we often write this as k dot x. So in modern language, this equation would be written as f of x is equal to integral dnk over 2 pi n over 2 e to the I k dot x. I don't know why that's happening. F tilde of k, where here x, Jesus Christ. Does anybody know why this is happening to me? Why it keeps going to erase? Anyway, here x is x1, x2, and k is k1. K1, K2. Well, we're just about out of time. Let me see if I can invite some questions here on the chat. Does anybody want to print a question on chat? I think I'm going to stop recording now.